Hello everyone, welcome to my YouTube channel, The Teaching Show. Please subscribe to my channel and hit the bell icon for more updates. And if you find this video useful, please don't forget to like it. Thank you. So let's start. And in this series of videos, we are developing a course on process calculation. So today I am going to take few problems on material balance without reaction on semi-batch processes. Now, in previous videos, we had seen continuous steady state, continuous unsteady state problems. Also, we had taken in last video batch processes. Today, we are going to see semi-batch processes. So, let's first understand what are semi-batch processes. So, those processes which you cannot categorize either as continuous or batch process, all of them come under this semi-batch processes. Okay. So you know that for a continuous process, there is an inlet stream, there is an outlet stream continuously flowing in and out. But however, if there is an inlet stream but no outlet stream, okay, this is the case which you see in most of the blending operations where you take some component in a mixer and then you add further components and keep on blending it. Okay, so such type of blenders you see in paint industry or distillery. Fine. So all these are semi-batch operations. Another type of operation is this type where you don't have an inlet stream but continuously there is an outlet stream. For example, in dryers and all, you see that solid is first loaded like a batch, but when it is heated, water is removed. Okay, so there is a continuous outlet stream but inlet stream is not there. Okay, so none of the material is coming inside the reactor, but material is definitely going out of the reactor. Okay, then there can be further complicacy. There can be two different phases or two different components. One component is continuously going in and out, while the other component is acting as a batch. Okay, you just feed some component, say this orange thing I am denoting over here. Okay, consider this, that it has been placed in the reactor or in the unit before before the process started, and then there is an inlet and outlet of second component, and then after your process has completed, then you open the unit and take out your component. So with respect to this component, it is acting as batch. With respect to this component, it is acting as continuous. So all these types of processes, they come under semi-batch processes. Okay, so let's directly start with the problem. This problem I have taken from Felder. This is a solved problem of Felder, but I have solved it in a different way. Let's see. Okay, so air is bubbled through a drum of liquid hexane at a rate of 0.1 kilomole per minute. The gas stream leaving the drum contains 10 mole percent hexane vapor. So hexane vapor is 10 mole percent. So mole fraction is 0.1. Air may be considered insoluble in liquid hexane. So none of the air is accumulating inside this drum. Use an integral balance to estimate the time required to vaporize 10 meter cube of the liquid. So you have to find out 10 meter cube of liquid. So liquid is depleting within the tank. When the air is flowing, it is taking or carrying away hexane liquid with it because of vaporization of the hexane. So you have to find out the time which is required when 10 meter cube of hexane has vaporized. They have given some physical constants like specific gravity of hexane is 0.659 and molecular weight is 86.2. So let's understand this problem first. Let's see what it looks like. Okay, so air is flowing continuously through the system. So I should use a differential balance. Differential balance means all these components, they are of the form quantity per unit time. Okay, now since air is not reacting with hexane, so generation and consumption term is 0, and air is not dissolving also in hexane. None of the air is dissolving in hexane, so whatever air is going in is coming out. So there is no accumulation of air, so accumulation term goes to 0. No generation and consumption, so your generation consumption terms goes to 0, and your balance equation takes the form input is equal to output. Okay, this is just for the component air. So we apply this. Input is equal to output for air. Input is 0.1 kilomole per minute, that is equal to 0.9 into n dot. N dot is the flow rate of the outgoing stream. So you find out what is n dot, that is equal to 0.11 kilomole per minute. This stream, it contains air plus hexane which has been vaporized. Okay, now let's see the other component, hexane. What happens? Oh sorry, this is hexane but I have written benzene, so just make it hexane. Okay, so hexane, it is not flowing continuously out of the reactor. We will still use differential balance, even though it says use integral balance, but what we are doing, we will write a differential balance and then integrate it. That's how we were doing unsteady state problems. See, in this case, since your hexane is continuously evaporating, so what's happening, this is an unsteady state problem, right? So I'm going to treat it as a unsteady state problem and use a differential balance. So let's write down differential balance, general balance equation. Input plus generation minus output minus consumption, that is equal to accumulation. Now since hexane is not reacting, so generation and consumption term is 0. Input minus output equal to accumulation, that is what is left. Now what you will see is that no hexane is coming into the system. Okay, it is only leaving. So input is 0. So what I am left with is minus output is equal to accumulation. Okay, so my balance equation takes the form output is equal to minus of accumulation, that is depletion, you can say. Okay, so balance equation now takes the form, what is output? Output of hexane is mole fraction times the flow rate. So 0.1 into n dot is my output flow rate, that is equal to rate of change of hexane within the system, and I am denoting it by minus dN by dt. That is the rate at which the number of moles of hexane are depleting in this vessel. Okay, so simple. That is how we were writing our unsteady state problems. Okay, I have just written balance equation and put it in terms of my variables. Okay, now let's solve it. So I am separating the variables, 0.1 n dot, that is equal to minus dN by dt, separating the variables, integrating it from say time 0 when we started passing air through the column. Okay, at that time I am saying that the number of moles within this column was N1. At certain time t, the number of moles were reduced to N2. Okay, so applying the limits, what I get is N2 minus N1, or basically N1 is larger than N2, and this minus sign will be accommodated. Okay, so N1 minus N2, that represents what? It's a change in the number of moles, or minus delta N. Okay, now we have been given minus delta V, that is equal to 10 meter cube. But we can use certain whatever physical values which we have been given, physical constants, I can make use of them and convert this delta V into delta N. Okay, so after integrating I got this equation. This equation gives you the difference in the number of moles, that is initial minus final, that is denoted by minus delta N. Delta N I can find out because I have been given delta V, because I have to find out the time which is required to vaporize 10 meter cube. So I am going to find out first what are the number of moles. This is volume, multiply it with density. What you get is mass, that is kg. Mass divided by molar mass. If m is your molecular weight, that gives you number of moles. So if I just multiply delta V with density and divide it with my molecular weight, I get the number of kilomoles which have vaporized. Okay, so I put this again in my equation which I have got after integrating this equation. I am putting delta N value over here, minus delta N value over here from this whatever I have calculated, and then I calculate the time which is required for vaporizing 10 meter cube of hexane. So simple. Okay, you have to just figure out where you have to apply differential balance and in which form your differential balance will be applied. Sometimes you might also have to apply integral balance. So I will again take this problem of tray dryer which I have taken in the last video. The same this thing, solid, a feed is coming 2000 kg, solids are 70%, water is 30%. The product which is leaving, it contains 99% of solid, 1% of water. Okay, air is flown through this tray dryer. Now I have added some more things. I am saying that air is coming at 80 degrees centigrade, and the outgoing air, it contains 2 mole % of water. Okay, now if this tray dryer has to finish this job within 2 hours, that is the drying time is 2 hours, then it has been asked how much air you have to circulate through this dryer. So you have to find out how much air you have to blow through this dryer at 80 degrees centigrade in order to complete this drying process within 2 hours. Okay, so let's break this problem again. If you have not seen my last video, please go and see that, because there I have taken the same problem and treated it as a batch process. Now I have complicated the problem a little bit, and now I am also doing a semi-batch thing. Okay, so let's see what is happening. First of all, with respect to solid, this is a batch process. Okay, because solids, once they are charged into the tray dryer, they are not crossing the boundary. So with respect to solid, it is a batch process. I am directly applying my balance equation since this is without reaction. So initial input, that is equal to final output. Initial input is 1400 kgs of solids, that is equal to 0.99 m2. So I'm calculating how much product is being formed, how much solid product or dried product I get directly from this one equation. So my solid balance gives me the dried product is 1414.14 kg. Okay, so water in dried product, that is equal to 0.01 into m2, because water mass fraction is 0.01. So water over there is 14.14 kg. So the water removed in this total process is 600, that is incoming, minus 14.14, that is going out. That becomes equal to 585.86 kgs. If I convert it into kilomole, I have divided this by 18, that is the molecular weight of water. So this gives me 32.4 kilomoles of water, or I can write it as moles. Okay, so this is the water which has been removed. I am saying that this is equal to delta N, which we will use in the following steps. Now let's say with respect to air, this is a continuous process. Air is continuously blowing in and coming out. Okay, if I apply my balance equation for a continuous process, my input is equal to output. So N1 dot moles per second are going in and N2 dot moles are coming out. Now these moles, they have air plus water component to it. It has been given that the mole fraction of water is 0.02. So just take this into consideration. So my mole fraction of air is 0.98. If I take material balance, N1 dot should be equal to 0.98 into N2 dot. Okay, now if I take water balance, just like in the previous example, what I have done, go and see that again. So my general balance equation and differential balance, it reduces to minus output is equal to accumulation. Minus output is 0.02 into N2 dot, that is mole fraction into the moles molar flow rate. Okay, that is equal to rate of change of number of moles within the unit. Okay, so minus dN by dt, that gives me the rate of change of water within the dryer. Okay, so I am just separating the variables now and integrating it, saying that initially I have Ni moles of water, finally I have Nf moles of water in the solid. Okay, so I'm just integrating it. I know Ni minus Nf, that is the amount of water which has been removed, that we had already calculated as delta N, and that came out to be 32,540 moles. Okay, so I'm putting this value. I know that this drying cycle, it runs for 2 hours, that is 3600 into 2, that is seconds. Okay, so just plug in all these values and I find N2 dot. Now I know N2 dot, I can use this air balance equation to find N1 dot. So I have calculated from N2 dot, I have calculated N1 dot, that is equal to 221.5 moles per second. Okay, now I have been asked to calculate what is the flow rate which is required. So I will further assume that air, it behaves as an ideal gas and it is at 1 atmosphere and 80 degrees. So I will just plug in this value in my ideal gas equation, and RT by P, that will give me my volumetric flow rate. Okay, so this comes out to be 6.41 meter cube per second. Please read the problem statement once again carefully by stopping the video over there, and then try this problem again. Thanks for watching, and don't forget to like my video. Thank you so much.